So thank you to the organisers of the workshop for allowing me to make an announcement in this distinguished gathering on behalf of the Ronald Davidson Trust. Ronald Davidson was a Cambridge mathematician whose life was cut short in 1970 at the age of 26 in a mountaineering accident in the Alps. His research interests were in probability, and specifically he was interested in stochastic geometry. The Ronald Davidson Trust was established by David Kendall and his colleagues and has since 1975 awarded an annual prize for young probabilists in Rollo's memory. So I'd like to take this opportunity to announce the winners of the 2015 prize. They are Nicolas Curien for outstanding work on random planar maps and related processes, and Jason Miller for far-reaching results on the geometry of the continuum Gaussian free field. Jason is presently in the US, but I believe Nicolas is here, and so congratulations.
We are a little in advance, but I think we can start with the scientific program. So the first speaker is Jean Bertoin from the University of Zürich, and he will speak about compensated fragmentations.
First of all, I would like to thank the organizer. It's a very exciting meeting to participate. My talk is about compensated fragmentations. And I will start by discussing the kind of a history of this notion. So this goes back to Kolmogorov in 1941, who was the first to introduce fragmentation processes. Kolmogorov worked in discrete time. The presentation I will make is on continuous time for a reason which will be clear later on. So to explain what Kolmogorov model is, so it's something about to describe the evolution of a process in which masses split independently and repeatedly as time passes. So it's convenient to introduce some notation first. So I will call mass partition. That will be a sequence P, P1, P2, and so on, where the PI's are non-negative real numbers. Pi is always, or P1 is greater than or equal to P2, and so on. All these are non-negative. And the sum of the PI's is at most 1. Okay? So a good way to think of a mass partition is to think of a probability measure on some space, and then the PI's are the masses of the atoms of your probability measure. And maybe there is a continuous part in this probability measure, and then the sum can be strictly smaller than 1. Okay? And I will denote by curly P the space of mass partitions. Okay? Then a dislocation measure is simply a measure nu on the space of mass partitions. Okay? And there will be further restrictions which will come later on. So to describe Kolmogorov's model, I will assume first, and for quite a time, that the total mass of nu is finite. And the evolution that Kolmogorov was interested in is fairly simple. So you start from an atom, a mass m, and this mass remains stable for an exponential time given with parameter given by the mass of the dislocation measure. So this time goes in this direction, and this has an exponential distribution with parameter nu of p. And so this can be thought of as a lifetime of your mass. And after this exponential time, the mass splits into smaller masses independently of the waiting time. And you have new masses, say, at m p1, m p2, and so on, where the mass partition p, p1, p2, and so on, has a distribution of the normalized version of the dislocation measure, so that distributed according to mu divided by its mass. Okay? And after the first dislocation, well, each of the submasses that you have obtained follow exactly the same evolution, independently one of the other. So that is, each one will live for an exponential time with the same parameter, independently of its mass, and then split again according to the same rules. So I hope that the model is clear. And well, this description reminds us of that of compound Poisson processes. Or that is random walks in continuous time. And let me briefly recall what I mean by this. Now the basic data will be a measure, which I denote by pi. It's a measure, and I will take this measure on the negative half line for simplicity. Assume that pi of r minus is finite. Then a compound Poisson process with a jump measure pi is a process which starts at some point, let's say for simplicity 0, and then it remains there. So I will denote this process by xi. It remains there for an exponential time with parameter pi of r minus. And after this waiting time, then it makes a jump. And the jump here is independent of the waiting time, and the distribution of that jump, so delta xi, will be given by the normalized version of pi. And then after this jump, where the process starts afresh, that is, you will wait again for an exponential, an independent exponential time with the same parameter, jump downwards and so on. Okay? Well, it turns out that, well, it's not just a coincidence, but fragmentation processes and compound Poisson processes or random walk in continuous time have a lot in common. And to see that more clearly, it's convenient to perform a logarithmic transform of a fragmentation considered by Kolmogorov. Because essentially, fragmentations have a multiplicative structure, and when you take logarithm, then you transform this into an additive structure. So if you take, let's say, x, it's the process, a fragmentation process, like before, with a finite dislocation measure. And then if you denote by chi of t, it's a random measure which you obtain by putting Dirac masses at the logarithm of the sizes of the fragment. So here, x of t is a random mass partition. It's x1 of t, and so on. Then the measure valued process chi of t is a branching random walk. And the evolution is, well, it's essentially seen here. You just take logarithm, so you have to consider the logarithmic transform of this picture, but it's essentially the same. So you start with logarithm of m, you wait for an exponential time, and then you replace, you imagine that your atom dies, and you replace it by a cloud of atoms, which are whose relative locations with respect to the mother particle has a fixed distribution. Okay? And in particular, if you want to find random walk in continuous time in a fragmentation process, then so you take this logarithmic transform, and you can follow, for instance, the largest mass at each dislocation. That is, you start here, then you decide to follow this one, and when this one dislocates, you follow the largest one, and so on. Okay. So so going back to random walks in continuous time, one of the most important chapters written in the golden age of probability theory by Kolmogorov, Levy, Khinchin, and many others concern limit theorems for sums of ID random variables. Or essentially, in our setting, it concerns constructions of extensions of compound Poisson processes in situation when the measure of the jump, the Levy measure, now we would say, pi, is no longer finite, but infinite. Okay, so that's done, work by Levy, Kolmogorov, Khinchin, and many others. So we want to have an intensity of jump which is infinite. And there is a first step that you can make in this direction is when you only assume that the integral of one infimum, the absolute value of x, pi of dx, is finite. So that's condition which I call 1. And what you do is the following. So you consider n of ds dx. This will be a Poisson random measure on 0 infinity times r minus, and you construct a stochastic or Poissonian integral with respect to that Poisson random measure. So you define psi of t is the integral over time between 0 and t and over r minus of x n of ds dx. And when the intensity, so I forgot to say that the intensity of my Poisson random measure is dt times pi of dx. So when you do so, well, you construct a well-defined process which does not explode, and because the Levy measure has support on r minus, what you obtain is a negative of a subordinator. That is the negative Levy process with non-increasing sample passes. Essentially, this condition 1 enables the measure pi to be infinite, but also involves a condition of integrability of that measure with respect to modulus of x. Essentially, it's a condition about the small jumps of the process. So it's a restriction on the intensity of small jumps of the process. So that's pretty straightforward to do. But what Levy, Kolmogorov, and Khinchin observed is that even when condition 1 fails, then there is still a possibility of defining interesting processes with independent and stationary increment. So first, let me stress that if one fails, and you try to apply this construction, then you get a process which explodes instantaneously. So Zt is equal to minus infinity, almost surely, for all t, positive. But nonetheless, Khinchin and Levy observed that under an assumption that I will write in a second, it's possible to prevent the explosion of the process by a deterministic compensation of the small jumps. So if now you assume that the integral of 1 infimum x squared phi of dx is finite, then the explosion can be compensated. And to be more precise, what you have to consider is, so you fix a positive epsilon, and you take the integral over 0t times minus infinity minus epsilon x, and you integrate it with respect to the compensated compensated Poisson measure, so that is n of ds dx minus indicatrix function that x is larger than minus 1 ds pi of dx. So this is a well-defined process, and when you let epsilon tend to 0, so this process converges as epsilon tends to 0 to some process psi t, which is a Levy process. That is a process with independent and stationary increments, and having only negative jumps, because the Levy measure is always assumed to be on the negative half-line. Okay? Okay, so if we return to our initial purpose, this certainly, well, we have seen that there are tight connections between fragmentations and random walks or Levy processes. This certainly suggests that our requirement that the dislocation measure being finite is too strong, and we might be able to define interesting fragmentation processes in which the intensity of dislocation is infinite. There are, however, some serious obstacles in such extension. Well, the first thing that you might try is, of course, to adapt the approach which was used by Levy, Khinchin, and others for the construction of Levy processes. And let me very quickly recall that this involves important elements such that, convergence in distribution of real valued random variables is equivalent to convergence of the characteristic function. So you need to compute the characteristic function of a compound Poisson process, and essentially you need to know the Levy-Khinchin formula to get. So it's essentially an analytic proof, but you rely heavily on characteristic function, Fourier transform, Levy-Khinchin formula, and so on. And all these tools do not really exist for in the space of mass partition. So you are stuck at this level. But nonetheless, about 15 years ago, it was proved that you can construct fragmentation processes with infinite dislocation measures, provided that this condition holds. It's integrability of 1 minus p1 mu of dp be finite. So remember that P1 is the largest mass in your mass partition. As we said, the condition 1 about the integrability of the Levy measure is a condition about the small jumps. And this condition is also a condition about smallness of mass partition. So what should imagine what is a small mass partition. When you split an object, you will say that the partition that you get is small when the largest fragment is close to 1. Okay, so this is a condition which allows mu to be infinite, but essentially it's restrict. It says that you can integrate, in some sense, the small dislocations. And in this, so that's condition which I will call 3. When 3 holds, then using deep results of, in particular of Kingman, about exchangeable random partitions, one can prove that there is an analog of this construction of subordinators or negative of subordinator given by Levy and Ito. So there exists a fragmentation process with dislocation measure mu. It's a non-degenerate one. And this, I will have no time to give any details, but there is also some Poissonian construction. Poissonian construction. Even though you cannot express things in terms of integrals of Poisson random measure, there is something which is similar to this Levy-Ito construction. And again, if now you want to extend this and construct more general fragmentation processes having dislocation measures which do not fulfill this condition, you try to apply this Poissonian construction which I made an allusion to, then you will get a process which explodes. So if 3 fails, then you get an explosion in the sense that the construction will produce a process in which the whole mass is entirely reduced to dust. You do not see any more large particles. So everything is reduced to dust. So that is, you reached immediately the trivial mass partition in which all the atoms have mass 0. Well, nonetheless, if we go back to what Levy and Kinshin did, well, I forgot, yes. So that's the condition which I have condition 3, I have condition 1, and you have understood that this is condition 2. So if we go back to what is known for the construction of Levy processes, well, we may think that maybe we can go a little bit behind this. And in fact, the purpose of my talk will be to show that you can still define fragmentation processes and prevent this explosion phenomena, provided that your dislocation measure now fulfills the weaker condition of integrability of 1 minus P1 square. Okay? And that's a condition which is, which of course will be referred to as condition 4, and which is an obvious analog of condition 2, which is here. Okay? And the idea is that essentially we will prevent this formation, this instantaneous formation of dust, by letting the masses expand and grow in a deterministic way. So we will prevent explosion by a suitable compensation. That is growth of the fragments. But let me be maybe a little bit more specific about what we are interested in. As we saw, upon this logarithmic transform, fragmentation processes can be thought of as branching random walks. So we have a branching random walk, and there are various regimes in which various regions of the space that we can consider. And very schematically, there is a supercritical regime. That is, when you are when you are expanding, dilating your fragment, you may focus on regions of the space in which particles are dense, asymptotically. So you will see plenty of particles there. And roughly speaking, the branching property tells you that these many fragments behave independently one of the other. So you are in a regime of the law of large numbers. And this was studied in depth in the setting of branching random walks by Begins. So in this region, you expect to have essentially a deterministic asymptotics. Well, that's not completely true, but because there is always this Malthusian martingale which come into place, but essentially results are deterministic. And there is also another region which is now subcritical, in which you are, with very high probability, sure of seeing no fragment. And then you are rather in the regime of large deviations. So here the space is empty, and you are in the regime of large deviations, and this is something which was studied by Alain Rouault, of course in much greater generality than what I'm doing. So, but my interest here will be really in the critical regime, and we will see that in this region, well, you have only a few atoms. I mean, it's really the stochastic process that you observe. You have only a few atoms, and it's very informally. It's the same as when you are in the work on branching random walks, the work by Bramson on the largest particle, or the beautiful more recent results which have been obtained by a number of authors in the recent years. So I'm really interested in this regime, in the critical regime, and want to observe of a stochastic process. Okay. So I would like to spend some time to explain the construction of these compensated fragmentation, and then maybe to explain how they arise as limits of ordinary fragmentation, just in the same way as general Levy processes arise in the limit of rescaled compound Poisson processes. Okay. So again, I will be assuming for a long time that the dislocation measure is finite. I will denote by x of t, so this will be my fragmentation process. x1 of t, x2 of t, and so on. And I will now expand, so this with dislocation measure nu. And I will transform it by letting the fragment grow at a constant rate. So there is a growth constant growth with rate c prime, and for some reason c prime is expressed in the form c plus the integral of 1 minus p1 nu of dp. Okay. So this will become, I will explain only later on why it is convenient to write things in this way, and the interesting parameter for us will be the c, not the c prime. So by this, I mean that I'm now working with another process, yt, which is exponential c times x of t. Okay, so every fragment is growing at the same rate. And well, you remember that for fragmentation, it's convenient to consider the logarithmic transform in order to rephrase the process. To rephrase the process as a branching random walk. So I will consider the process, the measure valued process yt, curly yt. This is the sum of the Dirac masses of logarithm of yi of t, and of course yi of t, so that's logarithm of yi of t is c times t plus logarithm of xi of t. Okay? Yeah. Sorry, c prime. Thank you very much. C prime. Okay. So I see that I have plenty of small chunks of colored chalk. So you remember that for ordinary fragmentations without growth, the trajectory remain stable, remain constant for an exponential time. So now in terms of the process y, you have introduced, so you start, let's say, for simplicity from 0, and the process grows, has a linear growth with rate c prime, and then it splits into, so it gives birth to smaller particles, let's say for instance 2 here, which in turn grow at the same rate and split. So maybe for instance this one will have just a single descent, and then maybe another time just one child, and then 2 children, and so on. And this one maybe just one child, and then 2 children, and so on. So this is the kind of picture that we have. Okay. And we can specify the parameters of the process very easily. So as I said, the the growth is just with rate c prime, and I know that the waiting time between until the first event will be exponential with parameter nu of p, and the distribution of the children after a birth event are given by the image of the normalized version of nu by the logarithmic map. Okay, so that's the description. And now we will do something very elementary, which seems completely innocent, but is a key to many things. So, with purpose, on purpose, I draw paths or dislocation events in which the mother particle gives birth to a single particle. Okay, so that's a situation in which there is a dislocation, one fragment. After the dislocation, you have one fragment, and a proportion of the initial mass has been reduced to dust. And rather than considering such event as a branching event, I will consider this, in fact, as a single particle. And so the lifetime of my particles are now possibly longer. Okay, so I really consider as a birth event fragmentation events in which you have either 2 or more children or 0 children at all. But each time I have just one child, I consider this as being a single particle. Okay? So we change our view. We slightly change the genealogy. And to describe now the process with this new point of view, it's convenient to introduce the notation P1 for mass partitions having only one non-zero element. So that the set of mass partitions P equals P1 and then only zeros, with P1 is between 0 and 1. Okay? So, with this point of view, we can now describe the fragmentation with growth process as we can view it as a, we can view Y essentially as a process indexed by the Ulam tree, that the union of n to the power k for k equals 0 to infinity, so that's the alphabet with infinitely many words, where n is a set of positive integers, n to the power 0 is the singleton empty set, and elements of this Ulam tree are used to give names to the to my particles. So to be more precise, this is particle empty set. This will be particle 1. This will be particle 2. And particle 1, you see, it lives here, it continues here, it continues here. Particle 2 is here, here. Oh, no, sorry, particle 1 dies here. And then you will have 1, 1, 1, 2. Here it's 2, 1, 2, 2, and so on. Okay? And so you can encode your process with 3 elements. So the first element, so I denote generically by U, this will be an element of my Ulam tree. So a particle U will have a lifetime lambda U, and this lifetime, so this is, for instance, for particle 2, this is this lifetime, and this lifetime will always be exponentially distributed with parameter nu of p minus p1. So it's a parameter which is possibly smaller than the initial one. You have a displacement which I denote by psi u. This is the displacement during the lifetime, during the life. And so in our setting, so that's the trajectory that you see here, for instance, in red. And therefore, it will be a compound Poisson process with constant drift C prime. And you have finally the jumps that you make at death. So delta U, these are the relative position of children. By relative positions, I mean relative with respect to the mother after the death of the parent. Okay. Now there is what is the outcome of such change of our point of view? Essentially, we had previously a static problem, in the sense that once a particle is born, it stays there until it dies. And here, well, we have started to introduce motion between the birth time and the death time of a particle. Okay, so the particles now are moving, not deterministically, because there are also negative jumps, which are random, And we have transformed the simple branching random walk point of view for fragmentations into perhaps a more complicated one, in which, well, you have particles move according to this compound Poisson process with rift, and then branch. Okay? So let me be now slightly more specific about the distribution of the compound Poisson process. So psi u is just a Levy process with Laplace transform psi given by psi of q is c prime q plus the integral of p1q minus 1 mu of dp. So that's an easy calculation. And by Laplace exponent, not Laplace transform. So by this I mean that the expected value of exponential q psi of t is given by exponential t psi of q. So the psi characterizes the displacement of my particles. Okay, so that's an easy calculation that you can do. And now I will use the assumption about the specific form that I had for the C prime, and I will rather write this as C plus integral over P minus P1 of 1 minus P1 mu of dp times q plus integral over p of p1 per q minus 1 plus q 1 minus p1 mu of dp. So that seems even more complicated, but maybe okay. That's also that will be also useful in a moment. Okay. Okay. So remember, our goal is to construct fragmentation processes for a dislocation measure nu, which fulfills some. I think it's still written here, which fulfill this integrability condition. Okay. Now, what I can observe is that if the measure nu is such that nu of p minus p1 is finite, and condition 4 holds, then the expression that I have above for psi makes sense, because condition 4 is the necessary and sufficient condition for the finiteness of this component, and the finiteness of nu on p minus p1 is well, tells me that this integral is well finite. Okay, so in fact, in this description, I do not need to assume that nu of p be finite. I barely need to assume condition 4 and this further restriction. And I can do it, in fact, a little bit better. I can, if I wish, I can also add some Gaussian, some Brownian motion, some Gaussian displacement, and this will be the Laplace exponent of some fairly general spectrally negative Levy process. Okay. So we are in a better position, except that now we have introduced this condition, the finiteness of the dislocation having 2 fragments or more, which we want to get rid of. Okay. Now the idea is simple, so we fix a positive epsilon, and we will consider a transformation of mass partitions. So to a mass partition P equals P1, P2, and so on, I associate the mass partition P bar epsilon, in which the first term is kept. Yes?
Should not have an integral over P1?
Oh, yes, sorry. It's about P1. And here, no, here it's really P. Yeah, here it's really P because it's, so this is, sorry, you're right. Of course you're right. I should know that when Jean-François asks a question, he's always right. Yes, it's P1. Thank you. Okay, so the transformation of my mass partition is the following. So I always keep the first fragment, but I retain the next ones only when they are greater than epsilon. P2 greater than epsilon times P2, indicator P3 greater than epsilon, P3, and so on. Okay? And I denote by mu epsilon, this is the image of me. So what I'm doing is that, very informally, as soon as I have a dislocation, I look at the mass partition which causes this dislocation, and I transform it. I will kill the small fragments arising from the mass partition. Now, if you do so, it's an easy matter to check that the measure nu epsilon fulfills the two conditions that we have. So that we have that nu epsilon fulfills the condition 4, and nu epsilon of P minus P1 is finite. Okay? So we can construct let's say a process y epsilon, which will be with characteristics 1/2 of sigma square, so that the Gaussian part which I introduced, C, this parameter there, and the measure nu epsilon. Okay. Okay, so all this has been a bit technical, and I have announced no result, so the results only come at the very end. So the reason why we chose parameters in such a way is for the following lemma. So this is an easy lemma. There is nothing deep about it. Essentially, easy calculation tells you that it works. So now, of course, you will let epsilon vary, and it turns out that you can construct simultaneously. We can construct all the y epsilon of t simultaneously in such a way that for epsilon greater than epsilon prime positive, then the measure, the point measure y epsilon prime at time t is greater than the measure y epsilon at time t. So there is nothing deep about it. You are killing essentially fewer and fewer fragments at each time. Okay? So this monotonicity is of course very nice when you want to take limits, because then you can define yt as the increasing limit as epsilon decays to 0 of y epsilon t, and this is what I call a branching yt. The process yt is a branching Lévy process with characteristics. 1/2 of sigma square C n. Okay. Nothing deep in this. But the difficult results, or more difficult results, come now. So the main theorem is that, okay, so here you see you have taken increasing limits because you are killing fewer and fewer particles. But when you take such an increasing limit, it's of course possible that you will fill the entire space, that the atoms that you create can be everywhere dense, and that's not a situation which you would like. So it's true, in fact, that P almost surely, for all T positive, the Yt of some interval A infinity is finite. So you have only finitely many atoms on semi-infinite intervals, and that's for all positive A. So in particular, we can rank the atoms of Yt in the decreasing order. And I will denote not the atoms, but remember that we had to perform a logarithmic transform in order to deal with branching random walk. So I will now invert this transform and consider exponentials of the atoms. And the sequence, let's call it Zt, that's Z1 of t, Z2 of t, and so on, of the exponentials of those atoms. Is in fact, it's not just a null sequence, but it's a sequence in L2. That is, that the sum of the squares are finite. So you get a process Z, or bold Z, Z of t. So this is a Feller process with values in L2, and I put a decreasing arrow to stress the fact that my atoms are always ranked in the decreasing order. And it fulfills, so it's a fragmentation process, it fulfills the branching property. Fulfills the branching property. And well, essentially the dislocations which arise in this process are done with intensity nu, and dislocations arise at rate nu. So that is, nu is really the dislocation measure that you wanted to have. Okay, so that's a result for mathematicians, but it's just in the sense that there exists something, we wanted to construct something, and we constructed it, but it's not so interesting if you cannot compute with it. And with this regard, there is an important function. So if we define kappa of q, that's 1/2 of sigma square q square plus cq plus the integral of the sum of the pi to the power q for I equals 1 to infinity minus 1 plus q1 minus p1 mu of dp. So this is a function which is well defined on the interval 2 infinity into R, and it's a function which resembles the Lévy-Khinchine formula, but it's not a Lévy-Khinchine formula. I mean, it bears some similarity, but it is not the Laplace exponent of Lévy process. And then the process for all q greater than or equal than 2, the process mq of t, which is the sum for I equals 1 to infinity of the vi to the power q of t times exponential of minus kappa of q, and this guy is a martingale. And in particular, this so you can take expectation, so you can find the expectation of the moments of your compensated fragmentation. Yes, of course, I forgot to, this was the main theorem. So the object that I have construct is the compensated fragmentation of the title. And to conclude, so something about Lévy processes which I had no time to mention, and which is nonetheless an important property, is that the distribution of the Lévy process depends continuously on its parameters, on the Gaussian parameter, the drift parameter, and the Lévy process, and the Lévy measure. And here it's essentially similar. So the distribution of a compensated fragmentation with characteristics 1/2 of sigma square c and u depends continuously. So I'm not sure, maybe I will not explain what continuously means. Well, essentially, it's something related to the weak continuity in terms of the dislocation measure, depends continuously on the parameters. Now, in particular, in the case when the measure nu is finite, so we have seen how to construct what are compensated fragmentations. They are just ordinary fragmentations to which you have superposed an exponential growth of the fragments. And this result tells you that limits of ordinary fragmentations with growth are given by those compensated fragmentation, essentially in the same way as Lévy processes can be viewed as a limit of compound Poisson processes under the appropriate assumptions. Okay. So Jean-François had no time to show the stop. So I stop.
There are questions or comments?
You take some sort of a scaling in the space direction in this. Is there a way to do this with time, perhaps by modifying the measure and trying to take...
Okay, so no, that's a very good question. As I explained at the beginning, in a sense, this study can be thought as an analog of what has been done for branching random walks, in which one studies large time asymptotics of branching random walks. In the setting of Lévy processes, this would correspond to convergence to a Brownian motion or to a stable process. Here we are doing something different. It's more closely related to the notion of triangular arrays in the construction of infinitely divisible distribution. In the sense that we do not accelerate time. Time is always, there is no rescaling of time. But what we are doing is that we are changing the intensity of dislocation. We are taking dislocation which become more and more intense. And in order to, so if we did nothing, then the result of having more and more intensive dislocation would instantaneously, in the limit, produce dust. So we compensate the intensity of dislocation by this growth of the fragments, and we do it in the appropriate way to see, in the limit, a stochastic process. So if we had chosen a different way of letting the particles grow, then we would have obtained results essentially due to begins if we had worked in a supercritical regime, or large deviation result of rho, which I explained at some point of this talk. Okay, but it's not. We do not accelerate time. What we are changing is the intensity of dislocation. So it's what you do when you are dealing with triangular arrays of independent random variables.
So do you have a way to characterize these compensated fragmentations maybe as the unique processes satisfying, independence and stationary increments in some sense?
Not quite yet. Okay, so that would be a different direction of research. Essentially, I know that these are the only ones you can obtain for binary dislocations. That is, when a dislocation occurs, then the mass m is split into m1 and m2 only, and the sum of m1 and m2 equals to the initial mass. So I know that these are the only one which you obtain, and okay, they have to fulfill, of course, the branching property and some homogeneity property. In full generality, I don't know yet. I suspect, yes, these are the only ones that I have not done a rigorous proof yet.